Continuing on from that last video lesson, we'll continue to talk about how to choose an appropriate drainage study design. There are basically three types of studies I would use to monitor conservation drainage practices: replicated plot studies, paired watershed or paired field studies, and in versus out type studies. I want to emphasize that our monitoring objective is pretty narrowly defined in this video. We want to do a field study, so not a modeling study, and our main goal is to assess how our given practice of interest reduces nutrient loss. We're also only talking about subsurface drainage, as you know. We'll start by discussing plot scale studies, which are a great way to study in-field practices like nitrogen management and cover crops. There are two key aspects here that make replicated plot studies effective. Firstly, a replicated plot design allows you to have many treatments that are replicated. For example, here at the Gilmore City site, there are 72 individually drained plots. A good number of plots allows you to test a number of different things as treatments, which is important for in-field practices, especially given the number of variations in nitrogen management approaches and the variation in cover crop species and management. And then replication of those treatments allows us to do statistics to analyze scientifically for differences between the treatments. The second critical aspect of this experimental design is that you're able to isolate the drainage from under every single treatment replicate. Many researchers use what are called border tiles or guard tiles to minimize the risk of lateral water movement underground between plots. For these studies of in-field practices, you want to have high certainty that the agronomic practice you apply to the surface is reflected in the tile drainage coming out of only that one plot. The Northeast Research Farm in Iowa is another prime example. There are 40 individually drained plots that are each 1 acre. A subsurface drain runs through the middle of each plot and then to a monitoring sump. It is not cheap to design and install and operate drainage systems like this. Doing replicated plots requires extra infrastructure and a lot of personnel time. One last one from Iowa. Even though there is inherent variability in the soil and microtopography, you'll see that for drainage studies, doing a replicated plot design allows you to take a traditional statistical view where you can, for example, block your treatments by soil type. Same site, note the border tiles used here in this design. And I would be remiss if I didn't show you a replicated plot site in Illinois that I have been involved with. The Dudley Smith Farm in Christian County, Illinois has 16 individually drained 2-acre plots. These are relatively large drainage plots where each plot has 3 lateral drain lines in it. The drainage laterals are spaced every 60 feet based on a 3/8 inch per day drainage coefficient. But even though the drainage system was designed to be extremely uniform, just remember there is natural variability in any field, for example, with organic matter and topography. My point is here that we do have variation in the amount of water leaving each plot, which makes the replicated aspect of these studies very important. You need enough replication, or in essence, you need enough statistical power to overcome some of the natural heterogeneity. The last thing I'll mention about plot scale research is that if you really want to geek out on drainage monitoring, and really who doesn't want to, there is a series of great videos available at the Transforming Drainage website, transformingdrainage.org. These videos primarily describe monitoring setups being used at replicated plots, which is why I mention it here. The thing that resonates with me when I watch these videos is that challenges like when the monitoring equipment is submerged or how you need to plan for frozen conditions. Is power required on site? Is earthwork required to install your monitoring system? What is the level of effort required for your personnel to collect samples and keep the site functioning in terms of sedimentation? All of these issues and more are mentioned many times across these videos. And all of these issues just illustrate the challenges of monitoring drainage water, and not just at the plot scale. Moving on to paired watershed, paired field, and backy type studies. This type of study is applicable for many of the in-field practices and drainage design practices. A paired watershed study works by you locating not just one, but 2 watersheds, or they could be fields, that are similar. You do your treatment in one of them, whereas the other serves as your control. And you monitor both of them and then compare the differences. The trick is that the watersheds or fields have to be very similar. Similar soil types, similar drainage systems, similar cropping management, everything similar except your treatment. The idea is that you'll be able to show differences in the water quality due to the treatment you implemented. These are definitely multi-year type studies because you lose the replication that you have with plot scale studies. So the replication in time becomes very important. A variation on this idea is called the BACI, or before-after control impact type study. This is where baseline data, such as flow and nutrient concentrations, are collected from paired fields for at least one entire crop rotation. After this baseline period, one field is designated as the control field and the other as the treatment field. And then, for the following crop rotations, the management practices in the control field remain the same, but you change the management on the treatment field, and you continue to monitor. In this example from Dr. Kevin King's USDA ARS group in Ohio, you see the two fields were managed the same in terms of drainage water management during the before period. The impact field and the control field had their control structures set to the same depths during that before period. But the after period shows the control and impact fields managed differently from each other. With a BACI study design, you assess how the response variable, like nitrate loss, changes over time from each field, and then you compare those changes to each other. For example, in this other study from Ohio, the slope of these two response lines from the two different fields were clearly different. This nicely illustrates that the control field experienced an increase in monthly nitrate loss, but the impact field, where alfalfa was being assessed, showed a decrease in the monthly nitrate loss. Rather than just looking at total loads or losses leaving the fields, you're actually evaluating relative differences in the relationship between those two fields over time. The suggested length of monitoring of both the before and after periods are shown here from the NRCS Conservation Evaluation and Monitoring Activity 201, which I mentioned in a previous video. The monitoring duration should be based on the number of years in the crop rotation. You can see even with the minimum, you're committing to quite a few years of monitoring. The BACI study design is a powerful design, especially for field scale studies. The strength of this approach is that it makes it possible to account for pre-existing differences between the sites, and thus allows us to estimate more closely the true effect of our treatment. And the last kind of study, and frankly, my favorite kind of study, is where you simply monitor the nutrient load coming into the practice and the nutrient load leaving the practice. This obviously only makes sense with edge-of-field practices, because edge-of-field practices like wetlands, pea-sorbing filters, and bioreactors are the only type of practice where you can feasibly sample water entering and water leaving. You cannot study a cover crop, for example, in the same way. At a bioreactor, you can collect a sample of the water flowing in by sampling from the inflow control structure, and you can collect a sample of the treated water by sampling from the outflow control structure. You can also use those same two structures for your flow monitoring devices. I've included saturated buffers and drainage water recycling in this category of in versus out type studies, but there are two nuances here. For drainage water recycling, the simplest method to estimate nutrient loss reduction that this practice provides is to monitor the amount of water that you store on site and the nutrient concentrations in that water. Those will roughly equate to your nutrient loading reduction for drainage water recycling. For saturated buffers, it's difficult to measure the out part of the equation because the water is filtering through the soil as reconnected shallow groundwater. We can relatively easily monitor the volume of water that's routed into the saturated buffer and the nutrient concentration in that water by taking advantage of the control structure. And then we use a series of monitoring wells to sample the groundwater as it seeps through the buffer. It's not quite as easy as monitoring a bioreactor, but of course I would say that. One last note, this ability to monitor the water going in and the water leaving edge-of-field practices is a benefit of this type of practice. You can have high certainty on the effectiveness of the practice because the monitoring design is relatively simple. Stick around for the next lesson where we'll talk more about data uncertainty.